Alright, so first of all, let's start off with what is SSVP? So SSVP stands for Steady State Visually Evoked Potential. Now that sounds like a bunch of jargon. And basically what that means is that when you're looking at a light that flickers at a certain rate, and that rate of flickering is between 3.5 and 75 hertz, that your brain can actually, or in your occipital lobe where your vision is processed, your brain will actually interpret that and resonate at that same hertz. So when we can measure these signals with EEG, as we heard from Dave's talk earlier, you'll actually see that the waves that are being generated on your scalp are actually going to resonate at the same hertz that LED or light was flickering at. So why would we want to use SSVPs? Well, they provide a good signal-to-noise ratio, so they're very easily classifiable. And when I show you an example later of what an SSVP signal looks like and how we actually classify them, you'll see that it's actually really simple and easy to do. And it's very easy to implement as well. You can do it with just simple LEDs flickering at a certain rate, or you can do it with a monitor. You can just put like a checkerboard pattern up on the monitor and it'll flash at a certain rate, and you can characterize it that way as well. So, how has SSVP been used before with brain-computer interfaces in the past? It's been used to control a rehabilitative arm for paralyzed patients. At the University of Bremen in Germany, they developed a system where you have like LEDs on top of this monitor, and you stare at them, and they will control this arm, and you can like drink from a cup that this arm can hold. At NASA, they developed an SSVP system where you can control a mouse cursor. At GTAC, which is a very famous company that makes BCIs, brain-computer interfaces, they developed a LED stimulation box that you just stare at and it'll control a mobile robot. Now, what we wanted to implement was a system that was a lot more intuitive in using SSVPs. So, I mean, the problem with something like the LED stimulation box is that you're staring at a box to control a mobile robot that's far off. It's not very intuitive, and you wouldn't want to just like go walking around with this box right in front of your face that's like 2 inches in front of your face all the time. So what we wanted to do was we wanted to think of like what's a novel way to use this. So we came up with an idea, and that was to play a game of checkers where each square would be lit up with that certain frequency that that would elicit the SSVP signal in your brain. So we wanted to interact with the physical world as well. So we didn't want to play some virtual game online that's been done a lot or check email. We wanted to actually use this to interact with our physical world. And we wanted to be able to have it interact with multiple players. So we can have multiple people playing the game, interacting in that same physical world. So another thing that we've done differently is that, so for instance with the LED stimulation box, the LEDs are always in the same place, they're not in fixed positions. But on our checkerboard, we light up the possible moves that you can make in the game. So the positions of the stimuli are always changing in an intuitive way, so you look at the square that you want to pick up the piece or place it at. And finally, we also want to, because the signal-to-noise ratio in this signal is so high, we don't need training in the algorithm that we implemented. We just applied a simple threshold, and it works fairly well across different subjects. So what was the environment like for our game? Sorry that the quality of this picture is so low, but we have the LED checkerboard in the middle here. We have 2 players wearing EEG caps, and we have a robot arm here. And in the background, there's like computers that do all the signal processing. And so let's take a look at the system design. And so first we have the LED checkerboard, and so this is what generates the stimulus. And once that stimulus is generated, what we do is we those signals are acquired by the EEG, and they're sent to an amplifier, and then we ship that off to the signal processing modules, which apply the thresholding thing that I mentioned earlier, and that sends it to the logic and network controller, which controls the logic of the checkers game, controls the robot arm as well, which moves the pieces on the LED checkerboard, and it also coordinates whose turn it is and basically all the logic that's involved in the system. And then finally, once the robot arm completes its movement, it sends the signal back to the logic controller to change turns or whatever and update the board movement. And then finally, it sends the the next set of movements to the LED checkerboard for the new set of stimuli. So let's first talk about the LED checkerboard. So we had a 6x4 board because to make things simplified, we only wanted to use 4 stimuli because using 8, the full 8, might have been too much for a first trial on this system. So when we use a 6x4 checkerboard, the maximum number of possible moves at any time for a given person is 4. So we can put either 10, 11, 12, or 13 hertz, assign one of those hertz frequencies to one of the possible moves. And so in papers earlier, they said that 40% duty cycle on the flickering elicits the best response for SSVP. So that's what we set the flickering rates at. And obviously we have transparent squares so we can see through the pieces and then see the flickering rate. And this was all controlled via an Arduino, which we were able to program over serial live. All right, so after the stimuli, how do we actually acquire the stimuli presented? How do we actually acquire the data? So, if you saw Dave's presentation earlier, he went through how EEG actually works. And so, for the sake of brevity, basically we had 2 different EEG caps, one with 128 electrodes and one with 64 electrodes, because that's what we had in the lab. We gelled up 8 of those electrodes in the occipital portion of the head, and that was because that's where the visual information is processed on the brain, so that's where we want to measure the electrical activity. We had a 256 hertz sampling rate, and we did this processing at every 8 samples, and we used a James Long amplifier for amplification. So just to give you an idea of what's going on, if this is your nose and this is the electrode cap, we use these 8 electrodes in the back where we can actually process the visual information. All right, so once the data is acquired, we'll need to then apply signal processing algorithms on it. So we do this with BCI 2000, which is the program that's used very generally for any BCI application. And then we sent the data off to MATLAB to do the actual processing. So we used a spatial filter where you actually calculate Laplacian derivatives because we want to get the best signal-to-noise ratio. And what this does is it cancels out some of the noise that you can pick up in surrounding electrodes. And this will generate the highest peak. And we'll see in a second what those peaks will look like. And so once we get a signal with the highest signal-to-noise ratio, we can take an FFT of it, and then we'll see that in our FFT that you will have strong peaks at the same hertz that you were actually staring at. So I have a quick MATLAB demo of actual data we took in the lab of that, so I'll show you guys that really quick. So you see in this figure, this is live, and what's going on is you're staring at an 11 hertz signal, and over time, this peak just shoots all the way up. Jeff?
How much time?
It depends on the person, but basically what we do is we say if this peak is 5 times bigger than the mean of the rest of it, then we classify it as that signal. So and also it depends on the ambient light, but it happens in about 1 to 3 seconds if it's dark enough, and if there's too much surrounding light, it happens in about anywhere from 3 to 15 seconds, something around that. All right. It's just since the hertz is staying consistent, the FFT is growing. That's why. And so if there's some inconsistencies in the wave, you'll see it start shrinking at a later time. So we're not taking a sliding window of this. We're looking at this throughout the entire sequence of when you started looking at it to, I think this was a 20-second run. So it just keeps growing at that rate. All right.
Is there a reason you don't take the sliding window? Is it better?
Well, because for our purposes, we don't need it to be live. We're just waiting for a classification to occur. Now, if it needed to be continuous feedback, then yeah, we'd put a sliding window on it, and that decreases the accuracy as well. So, all right. So classification, like I said before, we take the ratios of the signal at 10, 11, 12, and 13 hertz. So you saw that huge peak, and we take the mean power from 9.75 to 19 hertz. The reason we chose that range is because below 9.75 hertz, you'll see a lot of random activity from the brain. So that's where mu rhythms are found, and alpha rhythms, and a bunch of other brain activity. So we don't want that to muddy up our signal. And then 19 hertz, we stopped there because sometimes you can see harmonics from these signals if they're elicited. So if you get a harmonic on a signal that you didn't want to look at, that could kind of screw with your ratio as well. So we looked at the baseline from that range and then took the ratio. And then we took the average over all 4 of those spatial filters that we took. And then determining a priority by looking at a bunch of data, we determined that a threshold of 5 times is sufficient for our current project. And also what we do is that if the signal is just too muddy and we can't get a good classification out of it, after 20 seconds we reset it. And from actually playing the game, we've noticed that if in the first 20 seconds it doesn't classify, it almost always classifies within the next 20 seconds. Now that could be due to like movement artifacts that happened and that created like a higher noise ratio. But yeah, it generally works pretty well. So the next portion is the logic and network controller. So this is where all the checkers rules are implemented. It allows for multiple jumps, crowning. It can determine when the game is won. And also it gives you a choice in capturing. You're not forced to capture, which some checkers rules implement. Then it also implements communication and feedback to BCI 2000, determining whose turn it is. So it sends a stop signal to like player 2 when it's player 1's turn and tells player 1 to start. And then board controller controls the LEDs, which are lit up for the possible moves. So the first move, this LED would be lit up, and this LED would be lit up. And then you wait 2 seconds before a classification is actually made. So a player essentially has 2 seconds to decide which one they're going to move, and then they start focusing on that, and then the classifier begins to classify. When there's only one move available, there's no decision. The robot just moves on its own and moves the piece in place. And then finally, the robot is controlled over UDP signals as well. So the next piece of the puzzle is the robot arm. And so we used a Rhino robot that's actually used in one of the courses here. And so this would basically do pick and place procedures on our checkerboard, and also remove captured pieces from the board. And again, it would receive commands over UDP from the logic and network controller. So before we get into the results of this thing, let's actually see how this worked in action. So. All right, so this was the robot coming up from its calibration position. You can see that these 2 LEDs are flickering right here, and then after 2 seconds, the classifier starts and you pick the 13 hertz signal, which is right here, just from my gaze on that particular square. There's only one move, so it moves directly from there. So then the next person's turn, you can see that these 2 lights are flickering, one at 10 hertz, the other at 13 hertz. After 2 seconds, the classifier starts. It once again picked the 13 hertz signal. And then the player will have a choice again between these 2 spots. And then I think it picks the 10 hertz signal on. Yep, and then this moves over here.
Do you actually check how many moves are available? I don't think Flash does.
Yeah. Yeah. And so this was a capture taking place, and so the robot arm is actually removing the piece from the board.
Is that also automatic, like finding out how many moves are left, or you guys do that?
Well, it's programmed in there,
Okay.
so yeah. We don't. This is all like
Okay.
fully run by the computer. So all you have to do is just stare. And then, if you guys saw, the board was flashing B because black won. Right. So the results. Oh, Aaron.
If you talk while you're doing this SSVP, does that ruin signals?
Actually, I was talking actually a lot during that. If you clenched your jaw, then it would ruin the signals because there's just a strong neural signal that's being elicited from that. But if you just talk normally, it doesn't really affect the visual cortex. It would affect more like the frontal cortex and the frontal areas right there because of the muscle movements going on. But back here, it just doesn't pick up on those muscle movements. It's too far back. And that's one of the other advantages of SSVP. It's just really robust to artifacts, just random noise that happens. And so we were successfully able to play through a game. That was one of our goals. And actually, we were able to play through multiple games. And so on average, there were about 1 to 3 misclassifications per game, and each game was about 20 to 25 decisions that had to actually be made. So that's about like I think an 85 to 95% accuracy. However, in checkers, I mean, if you get one move wrong, that can throw off your entire game. So we're working on improving this, and in the next section we'll see like what the next steps are. So what are some of the issues that we found in this? We found that distance may affect accuracy. So the closer LED, so if you have multiple LEDs on the board, the closer ones appear brighter than the further ones. So even if you're focusing on the ones that are further, if the closer ones are too bright in your visual field, it still might classify that as that movement. So we're going to try and fix some of that issue. And also, light pollution affects the time to threshold. So if your surrounding environment is too bright, what will happen is that the accuracy remains about the same, but the time to classify takes longer because the average noise in the air or in the signal generated by the ambient light is raised. So the threshold overall takes a little bit longer to get to. So when there's no light, it's immediate, like pretty much 1 to 3 seconds after you start looking at it, it automatically classifies. And between subjects, the classification time seemed about the same. However, in dimmer light, it took about 3 to 40 seconds, and somewhere after that 20-second reset, like that I mentioned before. And one of the subjects had longer times to classify than the other one. It could have been the position of the light, or it could have just been how our threshold is implemented. But oh yeah, and we showed the video. So what's next? So we want to try and optimize our system, so find out what the limits of performance are. So maybe we can apply an adaptive threshold to deal with these distance and brightness issues. So for instance, in that same situation where I mentioned before, that more distant LEDs would have a lower threshold, so they would actually get classified more than the closer ones, which are brighter. And so what we want to do is we want to develop a probabilistic model saying that, okay, so what probability, or am I 90% or 95% confident that this will hit the threshold within a certain time, and then we can classify it that way. And then so some other things that we might want to add in to help facilitate the speed and the accuracy is that implementing feedback. So we can implement auditory feedback. So when you're looking at an LED, if you hear 2 sounds and as the peak of your FMT gets higher, those 2 sounds will come closer together. So you get some sort of audio feedback on how well you're focusing on the LED. So then we can have visual feedback as well. It could change the intensity as you approach the threshold, so it classifies quicker, or it could change the color to let you know how close you are to classifying a certain frequency. And also, if you were here for Dave's talk earlier, he talked about feedback-related negativity, which is evoked when you see an error in the game. So, for instance, if the robot arm picked a wrong move, it might elicit a feedback-related negativity signal in the brain, and we could use that as a kind of undo button in the game. And finally, since the range of SSVP is from 3.5 hertz all the way to 75 hertz, we can use a lot more stimuli in between. And the granularity of it is pretty fine. So I mean, we could do even like 11.2 hertz, and we could tell the difference between 11 and 11.2. So we could potentially have a full checkerboard in this system. All right, so the summary here is that BCI systems, like the one we just showed you, can be used to interact with the physical world, and we can do it in a very intuitive way. And so since the stimuli are modular, we can pretty much put LEDs anywhere we want in the world. They're very inexpensive, and they're very easy to wire up and light up. And the positions are not fixed, so we can actually change which LEDs are lighting up at certain times. They can be used anywhere as long as you can actually see the flickering. And then this opens up a whole world of practical BCI applications where you just focus on the region that you want to, and you can actually interact with the world in that way. And so acknowledgements, I would like to thank the lab for actually coming and helping me out and supporting this project. And this is a nice picture that we all took over the summer. And any questions? All right, Jeff?
Yeah, so what if you had like a heads-up display, like those, you know, Terminator style thing? What if you had like glasses, you know, they make them, they like, you can see through them, and you can also display stuff in front of your...
and...
in front of what you see, like overlay things onto your field of vision.
Lenses.
Oh, as a sort of like feedback communication?
Yeah,
like
augmented
augmented reality type of thing. So like you look at something and then it displays like something on your the visor or something?
I mean, the little example of the light box, and you're like, oh, you can't look at the robot, but if you have that, you can like have little arrows.
Oh, you mean like focus with your little visor on where you want to go?
Yeah.
I mean, I guess, but if you could implement some sort of computer vision where those positions could change, I still wouldn't find it as intuitive, because you still need to look in fixed positions for different things. But if you could have those positions change, then I think that's a really cool idea.
You should do it.
Aaron?
So, another way to track where somebody's looking is to watch the position of the iris. When is SSVP, when would that be competitive with eye tracking?
So the thing that's advantageous here is that we're actually able to, or that this response is actually elicited through focus. So when you actually focus on the thing, you can see that the peaks will actually get larger. So that's one of the things that actually one of our colleagues, Jamie, is working on, is that when you don't focus on it, the threshold, the peaks that go through the threshold are actually much smaller, and you can control that through focus only. So I mean, you don't need to move your head at all. You just need to concentrate on what you're looking at, and that's where this would be advantageous to something like an eye tracker.
How much somebody cares.
Yeah, exactly.
Which is something you can't do with eye tracking.
Exactly.
That's wild.
Any other questions? All right.
Okay, thank you.